Vision transformers have dominated computer vision, but their quadratic memory and compute complexity makes them impractical for edge deployment. Enter state space models, and specifically Mamba. By replacing self-attention with selective state space recurrence, Mamba achieves linear time complexity without sacrificing accuracy. But there's a massive deployment gap. The very mechanisms that make Mamba efficient on GPUs, like associative scans and heavy dynamic operations, clash with the streaming, bandwidth-constrained reality of FPGAs. Static quantization breaks down under Mamba's dynamic activation outliers, and low-bit weight quantization wastes precision on uniform grids. Today, we're breaking down ViM-Q, a scalable algorithm hardware co-design that finally cracks efficient Vision Mamba inference on the edge. The core problem starts with quantization. Vision Mamba activations suffer from two types of outliers: persistent channel-wise spikes driven by weight distributions, and highly dynamic input-dependent per token outliers. Standard static quantization can't handle this. If you calibrate on a small dataset, you're forced to use conservative scaling factors that clip rare but critical values during inference. To fix this, ViM-Q introduces a hardware-aware quantization pipeline. First, it applies per-channel activation smoothing. This technique redistributes the quantization difficulty from the activations to the weights by scaling them inversely. We fuse this smoothing directly into the weight matrix during offline calibration, so the hardware never sees an extra smoothing layer. Next, we implement dynamic per-token quantization for activations. Instead of a fixed scale, the hardware computes the real-time absolute maximum for each incoming token, deriving an optimal scaling factor on the fly. This maximizes dynamic range utilization and prevents information loss. For weights, uniform quantization at 4 bits is wildly inefficient. Most weights cluster near zero, but uniform grids waste levels on sparse tails. ViM-Q solves this with per-block additive power-of-two, or APoT, quantization. We split the magnitude into a coarse basis and a fine basis, combining them additively. This creates a non-uniform distribution that allocates higher resolution exactly where the weights live. But the real hardware win is computational. Because every weight magnitude is a sum of power-of-two terms, we can replace expensive floating-point multiplications with logic-efficient bit shifts. We process weights in small, independent blocks with dedicated scaling factors, isolating outlier influence and preserving fidelity across the network. Now let's look at how this translates to the FPGA architecture. The ViM-Q accelerator is built as a modular streaming pipeline. It processes partitioned input tiles immediately upon arrival, communicating through lightweight FIFO buffers to hide memory latency. The design hinges on two custom compute engines: a unified linear engine and a fine-grained pipelined SSM engine. The linear engine handles all dense projections. On a GPU, dynamic quantization and dequantization overhead can easily double the latency of a matrix multiplication. We eliminate that bottleneck by integrating the quantizer directly into the streaming data path. As activation tiles stream in, a parallel reduction unit computes the maximum absolute value, generates the scaling factor, and feeds it into a division unit that maps the data to 8-bit integers. Simultaneously, the engine leverages our APoT weights through a lookup table architecture. Instead of placing variable barrel shifters inside every processing element, we precompute the shifted results for each input tile once. The 4-bit weight magnitude acts as an index into these LUTs. A multiplexer selects the correct shifted term, a sign bit handles negation, and an adder tree sums the results. To preserve precision during accumulation, we left-shift the inputs by a fixed number of bits before processing, then right-shift the final output to restore the numerical range. This keeps fractional bits intact without bloating the logic fabric. The selective SSM module is where the real architectural innovation happens. GPUs accelerate SSM recurrence using associative scan, but that requires channel major memory traversal. Our FPGA streams data in token major order. Resolving that mismatch requires a massive on-chip transposition buffer, which burns BRAM and kills throughput. ViM-Q replaces the scan with a 3-stage pipelined engine that respects sequential recurrence while exploiting spatial parallelism. Stage 1 handles the state space update. We discretize the time-invariant transition matrix and the input-modulated control terms, then broadcast them across parallel processing lanes. The recurrence relation, H, T equals HT1, times the decay gate plus the control term, is fused directly into a single-cycle multiply-accumulate operation. Stage 2 projects the high-dimensional hidden state back down to the feature space through a streaming reduction. Stage 3 fuses the final output generation, combining the projected features, skip connections, and gating signals in a single combinational pass. By tiling along the state dimension and processing blocks of states in parallel, the engine adapts to varying model configurations without hardware recompilation. We implemented this entire pipeline on an AMD ZCU FPGA, running at 350 MHz. The algorithmic results are robust. At 4-bit weights and 8-bit activations, ViM-Tiny retains 74.2% top-1 accuracy on ImageNet, with ViM-Small and ViM-Base showing negligible degradation compared to full precision. The hardware benchmarks tell an even clearer story. When we benchmark end-to-end inference at a batch size of 1, the quantized GPU baseline actually runs slower than its full precision counterpart. Why? because calculating per token scaling factors and dequantizing weights on the fly negates the speedup of integer arithmetic. Our FPGA architecture streams through these operations natively. Across varying input resolutions, ViM-Q achieves an average 4.96 times speedup and a 59.8 times energy efficiency gain over the quantized RTX 3090. Even at higher resolutions, where the GPU begins to amortize its overhead, the FPGA maintains a decisive advantage in power efficiency, drawing roughly 12 watts compared to over 150 watts on the GPU. This co-design proves that algorithm and hardware cannot be optimized in isolation. Dynamic quantization requires streaming hardware to hide its latency. Low-bit weight representations require lookup table architectures to avoid logic bloat. Sequential state recurrence requires spatial tiling to bypass memory transposition bottlenecks. ViM-Q demonstrates that by tightly coupling these layers, we can deploy next-generation linear complexity vision models on resource-constrained edge devices without sacrificing accuracy or throughput. The era of edge-native SSM inference is no longer theoretical. It's ready for implementation.